Hello, I'm hoping you can hear me fine. Can someone unmute and let me know that you can hear me?
We can hear you.
Love it. Thank you. And I can hear you. That's a good thing. It's better than average. So what I'd love to do is to sort of switch gears on my screen and then maybe start to share a screen and then like just find out where we are at. Okay, share screen. That's over here somewhere. Okay, there we go. I found it. Okay. Yeah. Y'all did a midterm. Yay. And on average, the scores were pretty good. There's a couple of you who seemed like you struggled a little bit with the course material in chapter 5, which is honestly not unusual for a Stat 312 class. Like I said, probability is one of those things which uh most people don't get naturally, and it takes a little bit of effort to grab onto and feel super comfortable with. But your scores indicate happiness on average. And then in the cases of the couple who didn't do exceedingly well, in my opinion, you had some solid understanding in most areas, at least partial to good. So that makes me pleased. Second thing I want to mention is I guess we've officially completed as the end of the midterm. Um, 60% of the class time officially. And I guess if you don't count the day of the final exam as class time, we've surpassed 60% of the content. Okay, so that's another good benchmark. Uh, I guess I should say I think I've finished grading the exams, but I haven't looked over every single paper just to verify that I caught all the things I would want to catch by way of partial credit and or where students maybe had uploaded something. I want to make sure that I saw and looked over everything you uploaded. Because sometimes students don't indicate, oh, please see the paper that I had uploaded or the PDF that I had uploaded. And so I want to sort of go over and verify that I've gotten grades that are properly including all appropriate partial credit. I think there's another thing that is sort of cool about today, and we are officially switching gears, in my opinion, from the probability portion of the course to the statistical inference portion of the course. We tried to suggest last week at some point in time that probabilities asks questions like, hey, if I know all about the population I'm sampling from, what could the samples look like? How likely is a particular sample mean if we're sampling from, for example, a population that's uniform with an upper point of 100 and a lower point of 50? You know, the average is likely to be around 50. But then the question is plus or minus how much? Well, if you give me enough data points, we could use the central limit theorem and say, okay, now I know how to calculate a range of possible values, or I could tell you how likely any given possible value is for a sample mean. Today, we're switching gears and talking about a related question using the exact same rules, in fact. But the question we're tackling today is, hey, based on the sample we actually did see, what are the populations that could have produced it? So maybe it's a good time to sort of switch gears and show you a picture or two. And let's go with black. Essentially, we have a population, and I'm going to sort of draw this as though it's not necessarily normal, but looks like it's continuous. And there's some number out there, mu. There may be other characteristics that you would love to know about. Sigma is a good example of one such characteristic, a mean and a standard deviation. And if we take a sample of size n, lowercase n is almost always the sample size we're going to talk about, you get x1, x2, all the way up through xn. Those are the n data points. And you might get summaries like a sample mean or a sample standard deviation. And again, probability says things like, if you tell me about these, okay, let's switch gears. If you tell me about those guys and this, I might be able to tell you about how likely any particular sample mean X bar is to occur. And shoot, let's finish this and put S, a sample standard deviation. In statistics, we're going to go the other direction. Okay. If you are given X1, X2, X3, all the way up through Xn, and perhaps even something like X bar, a summary of that, and even S, a standard deviation of the sample, what is your estimate of mu? Well, we talked already a little bit about estimating mu, and we talked about bias or even mean square error. But how would you estimate mu? Most of you are thinking, well, just use the sample mean, because the sample mean, on average, is where the population mean mu is. But how far away could the sample mean be? We might very well want to say plus or minus how much? Plus or minus how much? Okay. So let's formalize this a little bit more, and we'll sort of slide forward into then a simulation and give you a rule. Okay. And I'll say that since X bar is on average, since the expected value of X bar equals, better yet, equals mu, X bar is an unbiased estimator of that unknown mean mu. Yeah, literally the expected value of X bar, if X bar is your estimate of mu, I guess I could write the expected value of your estimator of mu. Typically, if you put a little hat on top of something in a statistics, especially a lowercase Greek letter, mu hat, it's an estimator of the thing. If I want to estimate mu, I'm going to estimate it with mu hat. One possible estimator is X bar, and that's indeed mu. So we've got unbiased. Other possible estimators that you might want to sort of consider, at least by way of comparison, how about just using a different estimate of mu hat? I'll call it mu hat prime. I'm going to say, what if we have our mu hat being the third X? Maybe it's not the best estimator out there, but I'm going to, whatever you tell me your third data point is, I'm going to say, that's my mean. Literally, the expected value of the third X is also mu, also unbiased. But we did talk about mean square error and MSE. Okay, there we go. MSE, the mean square error, is equal to, well, the variance of your estimator, or better yet, theta hat squared, plus then the bias squared of theta hat. And indeed, in both cases, our bias here is 0, so we don't really have to worry about the bias term. You would want to go with the minimum variance estimator. Okay, so let's consider our estimator, mu hat, being just X bar. We know that the variance of mu hat, okay, the variance of X bar, if we're using that estimator, is just sigma squared over n. What about if we used our second estimator? We're switching back to the dark blue here. The variance of this mu hat prime is just, well, it's the variance of an individual X, and that's sigma squared. And which one's larger? I'm thinking the larger variance here is the worst estimator of the two. The smaller variance would be the better choice. In fact, if you're sampling in a simple random sample fashion, if you're sampling in a fairway from a population out there, the sample mean is the minimum variance unbiased estimator. Okay, there is no bias, check. And the variance is smaller than any other variance for any other possible estimator. So I'm going to sort of like hold there, take a screenshot real quick, if I can. Okay, there we go. Good. Got that screenshot. And now let's go ahead and clear that. Okay, so I guess what we'd love to be able to do. Oh, hold on. Let me stop and pause. I neglected to ask you a fairly important question that I should have. And let me just put a hold on this. Hey, are there any questions related to homework problems due tonight? I know there weren't people in office hours showing up to ask questions related to the homework problems, but I shouldn't just blow past that. I always want to pause if there are homework questions. Any homework related questions?
I don't think there was any homework posted for tonight.
Okay, that are due to sort of the second half of last. Oh, that's right. There, so I don't have to worry about it. I didn't screw up after all. Bonus point. Thank you, Megan. Then a question comes to mind. What is a range of plausible values for mu? And I'm going to write out a probability statement, and I'm going to assume we're sampling from a normal population at first. So I'm going to try and draw it as normal. Then I'm going to write normal. And there is a mean out there. And let's suppose for the moment we know sigma, the standard deviation of the population you're sampling from. Okay. Um, we know as a fact from that the distribution of the possible sample means the probability that X bar is in the range, and I'm going to go with negative 1.96 up to positive 1.96. That's 95%. Okay, so the reason I mention that is, well, you probably haven't internalized the Z table in the same way that I have. When I was much younger, we didn't really have computers to sort of key off of in this. Actually, we did have computers, but I didn't use them for this purpose. It's just a number that you may or may not remember. Okay. And remember how we did say if you go up and down about 2 standard deviations, you'll have 95% chance. This is essentially up and I need to do one thing to make this statement correct. I apologize. Let's darn it. Let's redo it. Okay, there's a population out here normal, and the probability that negative 1.96 is in the range X bar minus mu over sigma over the root of n. Yeah, there we go. That's correct. Up to 1.96. Okay, that's 95%. So you'd say 95% of the time, 95% of the time, the sample mean will be within 2 standard errors of the mean of the population. Okay. Literally, I guess I could rewrite this a little bit. That is negative 1.96 times sigma over the root of n less than or equal to X bar minus mu less than or equal to 1.96 times sigma over the root of n. That's still 95%. Inside the probability statement, I just multiplied everyone in sight by sigma over root n. And so, yeah, 95% of the time, the sample mean will be within about 2 standard deviations of the sampling distribution of mu. Now, I want to rephrase that a little bit. If I am standing close to the front desk in the classroom, okay, hypothetically, we're in a classroom right now, blah, blah, blah. If I'm standing close to the front desk in the classroom 95% of the time in class time, while class is going on, if 95% of the time I'm close to whatever your definition of close is, if I'm close to the front desk 95% of the time, is the front desk close to me 95% of the time? I would claim the answer is yes. It's just a matter of direction. Literally, am I close to that desk there, or is the desk close to me? The distance is going to be the same. The distance from me to you or the distance from you to me, it is the same. And if I'm close to where you are close to where I am. And so the fact that I viewed X bar as a random variable, which is likely to be in a certain range. I mean, shoot, let's even go a little bit further. That's a chance that mu minus 1.96 sigma over the root of n less than or equal to X bar less than or equal to mu plus 1.96 sigma over the root of n. That sigma looks really bad. Let me change that one. Okay, and now let me write in the sigma correctly, or better. That's 95%. Okay, so yeah, there's a chance that the random variable X in that range is 95%. But what if we put mu in the center and dealt with X bar separately at the lower and the upper end? I guess If I subtracted X bar from both sides, and let's go to lavender now, that's equal to the chance that negative X bar minus 1.96 times sigma over the root of n, less than or equal to mu, less than or equal to negative X bar plus 1.96 times sigma over the root of n, also 95%. Okay, so from the second line to the fourth line, which is subtracted X bar from both sides, and oh, that's a minus mu, I apologize. And because it's a minus mu, what I'm going to choose to do is to multiply everyone in sight by -1. So those negatives become positives. Let's make that negative a positive, also a positive. The directionality will change. I'm going to make that a positive. Directionality changes, positive. And that's going to be the only negative there. And I'm going to take the thing that's at the lower end and put it off to the left because I prefer that. The probability that X bar minus 1.96 sigma over the root of n, less than or equal to mu, less than or equal to X bar plus 1.96 sigma over the root of n, that's still 95%. We haven't really done anything other than change the ordering of the terms. We're saying instead of X bar is likely to be close to mu, we're saying mu is likely to be close to X bar. And by close to, we mean within about one of those. But that tells me a method of not just estimating mu with X bar, we could put a margin of error around our estimate that's going to capture inside our margin of error, it's going to capture mu, a large fraction, 95% of the time. So this essentially leads us to a 95% confidence interval for mu. And I guess this is the normal population. Sigma known case. Will be just sample average, plus or minus 1.96 times sigma over the root of n. That is a range of values that essentially estimates mu, and we have a plus or minus margin of error, or if you prefer, mo. I like The Simpsons as much as anyone, so let's go with mo. Okay, so we're estimating mu. We want to know what mu is. We're saying we're going to guess about X bar, plus or minus about 2 sigma over root n. Now, this corresponds to, we know sigma, and a normal population. Let's get some sense for how this really works its way out, okay? And what it means, how we interpret one of these confidence intervals before we go much further. So let me again clear this and switch gears. Okay, so you might have noticed inside of the week 4 content, okay, I say, oh yeah, there's this little simulation here that I'm going to use, this Rossmann chance confidence interval simulation. That's this guy right here. I've switched it over to means. The default was proportions. I switched it to means. If you are firing this up yourself, you can switch it to means. Normal distribution. We'll talk about other distributions later. And then I'm going to use a Z or a normal curve with sigma. Okay, as though I know what sigma is. And let's suppose the population mean out there is 0.5. In real life, you don't actually know mu. But for the purpose of this simulation to understand what's going on, we're going to say, let's assume we can do know mu, and it's 0.5. And let's suppose also that we know sigma is 10, and we're going to take a sample of 100 individuals. Sample size of 100, and we're going to do this exactly one time. So I'm going to do a sample. Hey, here's my sample mean. You can click on. Maybe I'll bigify. Hold on a second. There we go. Does it bigify? Okay, there we go. Make it a little bit bigger. My confidence interval here, I click down on it. I know that the sample average in my sample of 100 individuals from a normal population with mean of 0.5 and a standard deviation of 10, My sample was a 1.23243 mean. Here are the actual values with an average of 1.243. And if I go up and down, because we have 95% confidence, if we go up and down 1.96 times sigma 10 over the root of n, well, n being 100, I get a range of values that I think, okay, putting ourselves in a situation of, yeah, well, what if we didn't really know mu? What if I didn't really know mu? I would have a data set. These are the values. I have a sample average. I'm going to bet on that sample average. And my margin of error is literally go up and down a little bit from my sample mean. Okay. So we're going to do that. We're going to do it again. We can do it again. You can see across different samples, sometimes the sample mean will, with the margin of error, cover the true population mean. And sometimes it will not. I was hoping that I could find one. I did go by one already. And on average, if we're going to be right 95% of the time, we should be wrong. Like right there, perfectly timed. Notice that even if we go up and down a margin of error from my negative 1.595, my sample mean was so low here, okay, that even if I go up and down a margin of error, it doesn't quite include the true population mean. So what I want to do is sort of do a quick reset of that and say, well, let's just go with a whole bunch of samples all simultaneously. And I think 100 is a good way to go. So I'm going to go, what you and your 99 best friends all say, I'm going to sample from a normal population with a mean of 0.5 and a standard deviation of 10. I'm going to do that 100 times and calculate sample mean according to the equation we just saw in class, and plus or minus the margin of error, just like we saw in class. And you are lucky, your next door neighbor is lucky, etc. One of you missed, another, a third, even a fourth of you guys missed in the long run. That's going to happen. Some of you will be lucky, even if right close to the boundary. Some of you will be unlucky because you saw an unlucky sample. Okay, so what do we make of this? Well, in these 100, you and your 99 best friends, 96 of you hit, or you captured the true population mean mu in your sample, and 4 of you didn't. Bummer. Okay. What if we're going to do it again? And again, and again, and again, and again, and again, and again. So far, we've seen a whole set, 10 sets of 100 samples, and we're capturing the truth so far 934 out of 1,000 times, or 93.4% of the time. But probability doesn't allow me to stop there. Again, remember, we define probability only with the long run. So I'm going to go for, geez, this will take a while. Yeah, well, I'm halfway to 10,000, so let's go for a full 10,000. It can't take too long. Okay, 10,000. We hit 9,510 of the 10,000 times. We were successful 95.1% of the time at capturing the mean. In other words, in the long run, before we take a sample, this procedure, use the sample mean plus or minus 1.96 times sigma over root n, 95% of the time, you have a 95% chance of capturing the true population mean. Okay. There you go. 95% chance of capturing the population mean. So let me try one particular, actually, let me not try them. Let's talk about this one right here, right there. Supposing I corner you and say, okay, dude, what was your sample mean? And you tell me it was 1.336. And I say, what was your margin of error? And add and subtract that, you go negative 0.624 and positive 3.296. And let's suppose also that you don't know that mu is 0.5. What would you think? Well, you'd think, okay, I'm using a procedure that's right 95% of the time. but I don't know whether I individually did capture the truth with my sample and my calculations following the sample. What should you say? I would argue that due to the definition of probability, as statisticians, we can't say there's a 95% chance that we're right. That this guy right here with a mean of 1.336, a confidence interval, negative 0.624 up to 3.296, that person can't say there's a 95% chance that they're right. Why not? Even if they don't know if they're right or not, I will still tell you, this range includes the true mu 0.5. I mean, 0.5 is in the range, guaranteed. It's in that range. So that person is right. What's the chance that person's right? Well, they just got their mean. They got their standard deviation. Divide through by root of sample size. We have our procedure here. The chance that this person is individually correct, 100%. The sample being from the past means their chance of correctly capturing mu either was a hit, 100% chance of capturing mu after we've taken the sample, either you were right, or in the case of this other person over here, wrong. Even if you add and subtract your 1.96 standard deviations of the sampling distribution, okay, sigma over root n, even if you add and subtract properly from the 2.850, we're too high. We're above the population mean. Now, this individual schmuck doesn't know that they're wrong. Even with their margin of error, they don't capture that population mean mu. And so what does this guy think about it? This guy thinks, well, I'm using a procedure that's right 95% of the time. I'm happy with that. I'm pretty confident. I'm 95% confident that I'm right. And this individual is actually wrong. Which is, again, sort of a bummer. How do you know if you're right? You don't. How will you know if you're wrong? You won't. That's frustrating sometimes. As a professional statistician working with clients in engineering and agriculture and biology and all over the place, I've probably done about 200 confidence intervals in my life where I sort of did the data analysis for someone. And how often am I right? A lot less than 200 out of 200. I'll probably write about 190 out of the 200 because if it's a 95% confidence interval in the long run, I should be correctly capturing the number I'm trying to capture 95% of the time. So some of you might be wondering, why don't you want to go with a 99% confidence interval? I guess you could. And if you adjusted the confidence level all the way up to 99%, you could just see, oh, look, they're wider confidence intervals. Maybe if we reset this whole thing, and let's just do 1,000 all at once, that might be hard to see. But if I saw 1,000 separate confidence intervals that are each 99% confidence, we should be right maybe 990 out of the 1,000, about 99% hit rate. 1, 2, 3, 4, 5, 6, 7, wrong. 993 out of the 1,000 were correct. So it feels like we've got this procedure here that will correctly capture mu when we're sampling from a normal population with a known sigma. Do any of you have questions about that? I know I talked for a long time about that one, but I wanted to develop the whole concept. Any questions before we move forward at all? Okay, so let's tackle two separate other cases. One of them is, what if the sample is large? Okay, just the large N case. Shoot, lowercase n. Okay, come on. There we go. If the sample is large in size, okay, and what if it's not even a normal population? Well, you should be comfortable with that because, I mean, who really knows that the population you're sampling from is truly normal? None of us really do. So I'm going to draw that as non-normal. Mu and sigma out there. N is big. The distribution X bar distribution is approximately normal with mean mu and variance sigma squared over n. Okay, so in that case, we're feeling comfortable because we're looking right here at the same thing as we were looking at before. So essentially, if you don't have actual normality in the population, okay, but you have a big N, we feel comfortable. So some students would say, oh, do I know the population is normal? In which case, cool, I'm fine. I just need to know sigma. And other people would say, well, is N large? And whether you ask yourself the question about the large N first and then normality second, or normality first and large N second, it just doesn't really matter. It's if you have a not large N and a likely non-normal population that we really would be concerned. Okay. But so in this case here, things are as before. A 100, here's the more general way of writing it, times 1 minus alpha percent confidence interval for mu. And I guess alpha is equal to error rate. Think 0.05 for 5%, okay? Would be X bar plus or minus Z alpha over 2. That's the Z number, the Z quantile with exactly alpha over 2 in the upper tail. Times then sigma over the root of n. So let's talk about finding that Z alpha over 2. Because I guess sigma, if you know it, and n, you know it, I guess you're going to get X bar for free from the data. So how would you find that alpha over 2, Z alpha over 2? If you tell me you want to be 99% confident, that would tell me the error rate is 0.01, yo. And so if the error rate is 0.01, I'm going to have then alpha being 0.01. So Z alpha over 2, alpha being 0.01, alpha over 2 would be 0.005. And back on the homepage for the class, one of the things I linked you to was that Z, the standard, I guess the GMP probability distribution calculator. Let's go ahead, download and rerun. And let's, come on. Okay, I clicked is it bouncing? Okay, I thought I clicked this, but let's just go ahead and click it now. There we go. Open that, please. Yes. So again, if I input a probability in the upper tail and we claimed 0.005, that would correspond to 0.005 in that upper tail. That is going to correspond, if you will, to a two-tail error rate of 0.01. Okay. Same Z, negative 2.807, positive 2.807, or a central probability, a central chance of 0.99. Always we get the same Z. The Z that corresponds to 1/2 of 1% in the upper tail, or 1% between the two tails symmetrically, is going to have 99% in the middle. Okay. So if you tell me the confidence level, I can tell you the associated Z. And if you go from 95% confidence with a 1.96 to 99% confidence with 2.58, it just means you're going up a wider range. And that makes plenty of good sense because if you go out to, I guess, the pet store and you're sort of trying to find a fish and you look in the fish tank and say, I want that fish, the person who's then helping get the fish, they always grab a net and they scoop. If it's a little tiny net, they're going to miss the fish you want a lot. However, if you have a fairly big net, it's going to capture the fish just on one scoop. And if the net is so large, it's like 99% likely to capture the fish. You only need one scoop. The bigger the margin of error, the more likely that you're going to be capturing the true unknown population mean mu inside that confidence interval. Want to show you because on the final exam, you're not going to have access to this JMP probability distribution calculator. You could do that with the standard normal calc table. Okay. And here's one you could download one from anywhere on the internet if you want to, and just bring it to class for the final. And it's just a matter of you're gonna sort of go with an upper tail area of 0.005. Couple ways to do that. One of it is to note that there's symmetry. And if we find a Z that goes with that lower tail area of 0.005, the corresponding Z, when we drop the sign, would have an upper tail area of 0.005. So let's look for point in the interior of the table. 0.005, I'm sort of seeing 0.006, 0.0046. So I guess I'm going to read here to the right of the 0.00, I guess the 2.5, the negative 2.6. I'm looking for 0.005, and that's going to be somewhere in the range like 2.56 and 2.57. Okay. So yeah, 0.005 is going to be in that range. I'm sorry, 2.057 and 2.058, somewhere in the range there to there. Okay. So you could tell me negative 2.58. Okay. Go ahead and use that. Use either of them. It's not that big a deal. If you're ever in a situation where you need to get it exactly perfectly 95% chance, and the table says, oh, I can't give you exactly the number you want. All you got to do is use a computer. You're going to get it exactly. Okay. So the other thing we could do is remember if there's 0.005 in the lower tail, there's 0.005 in the upper tail, or 0.995, the 99.5th percentile. I could look for 0.995 similarly to find my right Z value. So I'm looking for 0.99, 991, 993, 995. I went too far, so somewhere to the right of this 2.5. 0.9951, 0.99449. So we're in that range, a positive 2.57 or 2.58. We're all good. Okay. So we're in good shape. We can use this method. Any questions about finding the Z value or the large sample size, possibly non-normal case? Okay. Well, what about the sigma unknown case? What if you don't know sigma? You're sampling from a population out there, okay? Again, and I'm going to draw it as not necessarily normal, but mu and sigma are both Greek letters, and we don't know them really. We're going to see a sample of x1, x2, all the way up through xn. I'm going to get x bar and standard deviation sigma. What we know is when the sample is large in size, X bar is close to mu. And we also know, for reasons that we hinted at in class, but didn't explicitly state, you could take a different stat class if you want the proof of this. We also know that sigma and S are close together as well. S is a good estimator of sigma. And so if sigma is unknown, but N is big, and by big, I think 30 or more, that's the way we always say it, our approximate 95% confidence interval for mu is, and this doesn't depend on whether the population we're sampling from is normal or not. It's just X bar, sample mean, plus or minus Z, well, I guess Z alpha over 2 for 95% confidence is going to be 1.96 times S over the root of N. We're just going to put in S, even though it's unknown, in place of the S that's known in place of the unknown sigma. So plus minus two standard deviations over root n, if you will. One term that I want to mention is that this last term, S over root n, is often called the standard error. Of X bar. That's usually implicit. So the standard error of X bar, sometimes abbreviated SE for X bar, it lets us know how close X bar is likely to be to the mean of the population that we're sampling from, and go up and down about two standard errors. This seems a good place to stop for the day. What we haven't talked about is small sample sigma unknown case. Okay. So I guess the solution today is just take a bigger sample. But in real life problems, sometimes you can't afford to take a sample of hundreds. And so you're stuck with, well, we've got 12 data points. What do we do with the 12? Well, we got a method for that tomorrow. So like before, what I'm going to do is sort of stop and say, enjoy the rest of your day, poke away at the lab, enjoy that, and we'll come back tomorrow, where if you have any questions on the lab or homework assigned today, we're going to pick right up. So I'm going to sort of leave this showing, unless one of you says you want to look at something else.
Would you want us to use 1.96 instead of just 2 for our 95% confidence intervals?
Good question, Sean. I would say yes, if we're in the large sample case, or if sigma is known case. If you have a small sample where sigma is unknown, but you have a normal population, we'll be talking about that tomorrow. So, John, I think I answered your question, but you clarify.
Yep, I was just checking in because in my previous stats class we just did 2.
Yeah, and to be honest, if someone were to on the final exam say, I don't have time to look up the proper number from the table, but I know I want 95% confidence, I'm going to use 2 instead. They're probably going to be doing something pretty reasonable. So I think I'm good. Any other questions? I'm hanging.
Uh, Hi, Professor. Can you hear me?
Hey, yeah. What's up, Anthony?
Hi, yeah. So I've just been at Costco getting my vaccines for the past 3 hours,
Oh,
and
geez, I'm sorry. Hopefully your arm isn't sore.
oh, it's I can't feel it, but that's all right. Um, so I'm in charge of submitting the lab for my team, and
Yeah.
I was hoping I could get a little bit extra time so I could make sure to review it and then do my due diligence on it.
Yeah, so send me an email and copy your lab members on it,
Okay. All
and
right.
I'll reply with, that's good. No
All
problem.
right. Thank you. Should I send it with the submitted lab completed or should I send it before?
I just send an email right now, real quick, and copy
Okay.
your group members, and then I will reply with, no problem. Don't worry about it. And
All
then
right.
they'll feel a sense of reassurance as well.
Okay. Thank you, Professor.
Mhm.
Have a great day.
Mhm. Hey, Paulo.
Can you hear me? Oh,
I can now.
sweet. I have a question. Did you say there was homework today? Due tonight?
No, I thought for a moment that there might have been, and then uh Magna reminded me that there wasn't.
So the
So
next homework is going to be 7.1, 7.2 for sure.
yeah, yeah,
And then
exactly.
whatever else tomorrow as well, right?
Exactly, yes.
Perfect. Thank you.
Uh-huh.
Have a good
We'll
one.
see you soon. Bye-bye.